Okay, Jessica, I tried to contact you a while back and see if we could move this to 5 p.m. We're kind of busy here at the house in Virginia right now. My father did pass this morning and we're cleaning up. So I want to record this for you. Of course, we'll convert it over and make sure you get notified that you're going to get the link to the video. In the last class, we talked about a bunch of different topics that are related to this week's work. And the first thing I'm going to do is actually bring up not that, this one here, the assignment for the week. And I'll get that shared with you in a moment as soon as it comes up. But I wanted to just do this ahead of time. Come on, wake up. Thank you. So I talked about, no, that's the wrong assignment. How did that happen? My apologies. That was the wrong one. Let me get the right one. Okay, so here's the week 3 assignment that we had, and we're looking at a variety of different of things. We talked about the material related to probabilities in questions 3, 4, etc. I want to talk about what we do for answering the first 2 questions of this assignment. So we will, I will then come over here and go back to what we'll talk about for today. The reading, I'm going to take all this from the OpenStax book, the PDF text. And this is from chapter 12, which starts on page, whatever it is, 679. And we'll talk a couple of things first. I want to remind you about linear equations. Linear equations are equations that if you graph them, x and y values, they would form a straight line. And basically, regression and correlation require us to try and find a straight line relationship. And we'll talk about how that works in a minute. But I'm going to remind you of what a straight line equation was. Remember from our algebra, we used a slightly different notation. They say that here the straight line is a plus bx. And in our algebra class, remember that was mx plus b. So the confusion here is that this should be b plus mx if you're going to look at our algebra. Where this in their notation here, and I'll stay with that because they use it throughout the chapter, A is the point at which the line crosses the y-axis. Remember the xy coordinates, the y is the vertical and the x is the horizontal. The point at which they cross is 0. Everything to the left of, or to the right of that 0 point is a positive x. Everything to and above that 0 point is a positive y. So it's divided into 4 quadrants. The b in this is the slope of the line, meaning how far up or down the line goes as you move from left to right. If the line goes up, we say the slope is positive. Think of it as walking up a ski slope. It's hard to walk up, so walking up is a positive slope. Down is a negative slope, meaning that it's lower on the right than on the left. So we look at any kind of linear equation where we have a numerical value followed by a variable term that has an x in it. This is a linear equation. Okay, so this other example here is indeed a linear equation. In this case, in the case of this 12.1 example, the point at which the line crosses the y-axis is minus 0.125, and it is a downward slope, and the slope is fairly steep. 3.5 is the slope, so it's a straight line. And we can graph those. Let's go to the next page. If we look at the one equation here, let's go back to the previous page. Minus 1 plus 2x. So the y-intercept is at the minus 1 value and the slope is 2. If we graph that as a straight line, then we find that indeed the line crosses here at minus 1. And if we could calculate the slope, we would see that it was actually 2 times x. A linear equation is always a straight line, so anything that's curved is not linear. So this graph shown is not a linear graph. Anytime you have the y-intercept and the slope, you can calculate a straight line. All you need is 2 points on a straight line. And your equation, y equals a plus bx, we know what a is. That's the place that it crosses the y-axis. So that's 1 point. And if we decide that we want to find out what a second point is, all we have to do is set y at 0, or set a at 0, and then y would be the slope times x. We know the slope, and so we can calculate using a. We can calculate what the point at which the second point is going to be. So we can do that very quickly by setting x equal to 0, which is the point at which the point at which y is the y-intercept is at x equals 0, and then we can then plug. We know what a value there is, and we can use the equation then to calculate a second point, and then we know what a straight line is. So that's all we ever need to draw a straight line. Scatter plots or dot plots are something that we use in this analysis to do a regression analysis and correlation. Correlation merely says asks the question, is the variable x and y, are the changes in those values related? And although if you have an equation, then definitely they are. But if you're talking about raw data, you can have scatters all over the place. Let's go down here to look at a couple of other scatter plots here. And this is some values of x and y, and these are all just determined. So we're looking at what is the value of x for a value of y. And you see it's not a perfectly straight line. And quite frankly, most of your data will not deliver you that perfectly straight line. We can also have a major deviation. Look at this value of y over here compared with a value of x. When you go up higher on x, y is much, much lower, but the rest of the line is linear. If you were being a scientist and looking at your data, you would question whether or not this one that's really deviating from the line is a real measurement. And as I said before, if you can't prove that it isn't, you have to include it. So we have, this is what we call a strong positive linear pattern. It looks like it's going straight up. And this is a strong negative pattern. It's going very, very much down to the right. And a pattern that sort of looks like it's, going down, but it's kind of weak because you've got some big variations in the value of y. So there can be very weak interactions. Let's keep going a little bit here. If we look at this example here, which is relating the final exam score to the exam score of the third exam in a term, and are they related? That is a question that people have. So if we look at this, there is apparently a relation, but it's kind of weak. We've got one very, we just have these various student scores here, third exam score and the final score. Note that the scales don't have to be the same. We just want to see if there is a relationship between how well people do in the third exam and the final. And indeed, it looks like there is a relationship. Okay, so if we keep going, I want to do this fairly quickly. This is another one where we have a much lower slope. Although the values in this scuba maximum dive time versus the depth in feet should actually be fairly well related, and indeed in scuba diving they are. So what we have is again a plot of this data. Going to keep going. I'm not going to go into how this is done. So the third exam score versus final, slightly related. It's definitely related here. And then let's look at calculating. If we do this calculation using a formula that can be derived, we find that that the value is that we do find a linear equation, minus 173.51 plus 4.83x. We're not going to go into this stuff that goes into some of these other kinds of things. We won't go into a lot of stuff, but let's see if we can look at what's called the correlation coefficient now. The correlation coefficient is a measure of the strength and the direction of that linear association between x and y. There's a complicated formula for calculating it, which in the same way that I talked about before is best done using Excel for doing those calculations. And the value of R is always going to be, of the correlation coefficient R is always going to be -1 and +1, meaning that If it's -1, there's a strong negative correlation. And if it's +1, there is a very strong positive correlation. If it is 0, there is absolutely no linear equation. Most of the time, you'll find your data will be that has no correlation will have a slope that's very close to 0. A 0 slope is a horizontal line. So the value of using the correlation coefficient tells us what is whether there is any correlation and what it might be. So if we look at the next page, we have some scatter plots showing a strong positive, a strong negative, and 0. We have a perfectly horizontal line. If you look at these things, they just happen to have data. Computer spreadsheets will do this. So we won't go into coefficient of determination. What is the significance of this is to decide whether the sample that you've taken and you get your correlation coefficient, if you can really literally model that relationship in the entire population. So the closer that slope is to 0 and the closer R is to 0, the less confident you are that you can take the data and correlate it to the entire population. Okay. If it's there is and basically what we have is sufficient evidence. Let's go back up one page. If we look at some of the data here in the example that they gave us on that third example, in the third exam, final exam example, correlation coefficient is 2/3 basically, 0.6631. And the coefficient of determination is the square of that, which is then 0.4. So approximately, what this tells us is that about 44% of the variation, it can be explained by variation in the third exam. Therefore, 56% of that variation cannot be explained by variations in that third exam. So what we have is a way of looking at that, but we can look at the correlation coefficient and say there is a relationship, but how strong it is and how much of it is a little bit further than this course has been going. You're not going to be doing the coefficient of determination in this class. You will be looking at the correlation coefficient. So we'll go to figure out how that calculates in a bit. And that's about as far as we're going to go. Let's take a look at a couple of other things. So what if what we have here really is looking at an idea as to what the sample coefficient, to determine whether the correlation coefficient is significant or not. And when we look at this, we look at this as being if R is between about 0.63 and -0.63, we are saying that that R is not terribly significant. And if we look at our calculated, this is a statistical formula. If we look at our actual calculated value, just a second. Okay. we look at our actual calculated value and determine that it is higher than this 0.632, we consider it significant. So that's our criteria for determining these things. Let me just keep going. Okay. Outliers are examples of data points that are far away from the least squares line, and the least squares line is merely that line that we calculate for the correlation here, in looking at the data. So if we look at the data here, we had remember our first point in that plot of the data points of final exam score versus third exam score. The very first data point, the final exam score, was very much higher than the third exam score. We can look at this here. In fact, the third exam score was like 64.5. The final was like 175, it looks like, or 178. I don't have the thing in front of me. So that we do have outliers that are that will appear. And what we can do is actually draw some parallel lines away from the actual least squares line that we calculate. And they have to have the same slope as which is by definition, since they're parallel. So we do this several ways, but if we look at the two extra lines here, we find that most of the data points will fall between these two lines. I'm trying to remember, trying to show you where they describe how they calculate it. We're looking at something that is the starting point. The lines are parallel, but if we go back to taking a look at the data and calculate the standard deviation, remember the standard deviation rule is that 95% of the data will fall between plus and minus 2 standard deviations of the norm. So this line, upper line here, is 2 standard deviations above the mean, and the lower line is 2 standard deviations below the mean. So we've calculated that slope and made these lines parallel. Outliers will fall either above or below these parallel 2 standard deviation lines. This one just barely does, but that doesn't mean that it's not. So it is close to the line, but it's not. It's going to be considered a significant outlier, less than 5%. This is another set of data that has had a regression line calculated, and the fact that these other points, we haven't placed the other, we don't have the raw data, but the 2 parallel lines here are the standard deviations have been calculated, and that's 8.6. So 2 standard deviations from this point, where the y-axis, this is about 76. So 2 standard deviations below that is going to be 17.2 from 76, which is 17 from 76 is 57 or 56. So this would be 55.2. And if we look at a parallel line that goes starting at about 55, this data point clearly is an outlier. Lots of ways of looking at that. So, so does the outlier affect the line? Yes, we have to look at the fact that we've included it. So the question is, do we exclude that particular data point? And that again is, we're not going to go into why, but we do want to examine the data to see if there are any problems with it. If there is, we can fix it. But if there is no way to fix it because we can't redo an experiment, we can simply delete it. But we need to note that that piece of data was deleted from the calculation. So I think that's all we're going to worry about in this chapter. So let's go back to now the spreadsheet for this week, which is this one. Okay, so here we have X and Y. We don't care what X and Y are, but the Y values are here and the X values are here. And the values are all over the map, as you can see here. So what you want to do is calculate the slope and the intercept. Now, let's do one quick thing here, and I'll show you how the formulas are used to do this particular set of calculations. We'll calculate the y-intercept first. So you'll note that we highlight the y's, okay, and that's put in. Then we do the same thing with the x's. So we, no, that was wrong, sorry. So then we click in the x's box and then highlight those, and we get these two ranges. And what we'll get, we already see the result here, so I'm just gonna do that. So that's the y-intercept. In other words, down here at -6. So we know that. Now we want to go into, what we'll do is move to a different spot. We'll go into one more, which is the slope. We bring that up. Again, we input the y's into this field and the x's into this one, and we'll get an answer. I'm going to let you do that rather than actually do the answer. Note that when you make a mistake, it gives you an error. So the other thing you're going to do is calculate the linear coefficient, the correlation coefficient. And that is using this one called Correl. And again, we have the two of these, the cell range for these. So we've got array 1 and array 2. This is called an array of data. So we can place either one anywhere and it will give us that correlation. Usually we want to start with the y's first and then the x's. And it will give you that correlation coefficient. Now, I'll let you do that on your own as well. Yeah. Get rid of that. All right, you're being very resistant, aren't you? The other thing that your instructions tell you, let's go back to those right quick. is, here we go, is using, take Microsoft Excel and graph this line of best fit using the trend function. Well, let me give you an idea as to what the problem is there, because it really doesn't work exactly the way they imply that it works. If we go here and use trend, we'll go over to the statistical functions, take trend. So we have our known Y's. No, we don't want to do it that way. Cancel. We want to go over here and do trend. Again, it doesn't give you a very good idea as to how to use this. And the help function in this is useless as far as I can see. So we've got the known Y's and the known X's, and we're going to ignore this constant thing here. The new X lines, we're going to put in here and see what we get. They don't like it. That doesn't surprise me. So what we will, so it doesn't like doing that. So here's what I have discovered will work to a certain extent. We put in the known Y's and the known X's for this one, and we calculate a value. So that's for the first point. Now, what we need to do is come up here and actually tell it to go from the Y values of B to B, and we'll put a $ in here to tell it to fix that. Because what we're going to do now is we'll get the same value, but what we want to do is copy and paste all the way down the line. And it didn't like that. It did this to me before. Okay, so don't bother. I fixed this at one point. Okay, so maybe I did it the other way. Okay. Okay, so let's, let's copy this. So I fixed, what I tried to do is give values that worked. It doesn't like this either. So this is not clear what it's trying to do for me. Let's try that. Okay. All right. So now we have, so what I did was I fixed the value of the end point of the X data set, of the Y data set. And then I fixed the endpoint of the X data set as well, because it was going to keep on trying to move down the line. Every time you went down, it would try to put another value, which is going to be a null value. So it will calculate these. The problem is the last several data points get crazy. So this is the best I can do. But if you look at this, most of the data pretty much follows a straight line. If we leave out the last couple of data points where it gets a little wonky, then we have a better line fit. So it roughly, and if you look at this, it looks like it goes down to about -7 or so, which is about what we calculated for our y-intercept. But the problem comes in when you have a data set, when you have two x values of the same value, but two y values that are significantly different. And we have those at 3 points in this data set. X equals 24, there are two values that are somewhat different, 19 and y is 19 and 25. It gets very much different when we get to x equal 29. We have two of those, and we have a y of 4 and 42. So it's trying to calculate numbers that just can't correlate very well. Then we come down here, we have two values of x equal 37, and we have 40 and 67. quite a bit of difference there as well. But not near as much as for the y equals 29 value. So I don't quite understand this. I've not been able to get anyone who can tell me why this doesn't work, other than Excel just doesn't do this one very well. So you can get there. So I'm doing this to show you why you don't want to mess with the trend, but what I really want you to do is give me a slope and a y-intercept. So let's go back to that question again. Back to the assignment again, the written assignment. Let me find it. It's week 2, week 3. No. Don't want that. Week 3. So it tells you to use the trend. So you're going to find the slope and the y-intercept, and use that to give me an equation: y equals mx plus b, or y equals a plus the y-intercept plus the slope times x. So go ahead and calculate those things and give me an equation. But don't try to use this trend. It will just frustrate you. It's taking, every time I do this, it gives me some results that don't make sense. So there is a difference in those assignments. So let's go back to the class here, and we'll just back up a little bit. Obviously, we have this week's we have the week's discussion, and we have an assessment as well as the assignment to do. So go ahead and finish out that work. And what we'll do is, if we can possibly meet again on next Tuesday at this same time. Let's try 5 o'clock. Go ahead and tell me if that's going to work for you. If not, that's fine. We can meet whenever you're available on Tuesday evening, and do the have a class for the last week and get started on that on variance. And we'll get that done, and then meet regularly at the regular time, 6 p.m. on Thursday, when I should be back in Colorado. So go ahead and after you've watched this, send me an email, and the code word for this class will be Zurich, Z-U-R-I-C-H. So go ahead and send that to me. If you have any questions, email them, and I look forward to speaking with you next week on Tuesday night and then Thursday.